overall, and also possibly you reflecting on what went okay, what didn't, and maybe to motivate you to go back and look at what didn't go wrong well. So the muddy points mainly are on PSD. So that is the concept that we covered last, and I admit that I rushed through it. So we'll talk a bit about that. So I'll just touch upon what is this power spectral density. So what we are aiming at again is to understand the distribution of power in this acoustic signal across frequencies. So that is the meaning of spectral analysis, that you want to find out distribution of power. Again, we'll see that power is the correct metric to be looking at across frequencies. Now, if it were okay, so we will get to tangentials later on. So, what we typically get in a very uh, highly filtered version would be a very nice curve like this of PSD as a function of f versus f, and it will tell us many things, including, say, if you were to be interested in what is the power within a particular band of delta f starting from f1 to f2, then the area under this curve will be the power in the signal, and you will notice that I have not started from the y axis. Why is that? So, okay, any other ideas? Something else? Why are we not starting from the 0 of the frequency axis? Why am I not plotting from that? This is log of frequency, so log of 0 is not defined. Okay. That's why we cannot draw it. So remember, we are typically plotting on the log frequency scale. Okay, it's just a trick question to get you awake. So how we get this, you will find in the notes. If it was not clear, again apologies for that, from last class, then you will get in the notes how we get this. So essentially you take the Fourier transform of your pressure, then you take the absolute value square of that, then you multiply by some magic factors sigma slash chi, some magic factors you multiply that by, and then you so this is of course at a particular frequency that you take the Fourier transform, and you plot that. So that is the mechanics of it. The details of why this means the power spectral density is again in the notes. So it has to do with the Parseval's theorem. So those of you who have read the notes would recognize this, and you should also recognize this from your engineering math courses about Parseval's theorem. What is Parseval's theorem? In broad sense, what does Parseval's theorem state? Correct. So if you were to look at a signal P versus T, so what is the measure of power here? It's a PRMS square, or the variance of the signal. So because this is real, in general, you will have PR hat versus frequency, and P hat are P hat I, the imaginary part and the real part of the Fourier transform in frequency. How might these things look like? How would you typically plot these? You have to go to negative scale also. Okay, so they will typically have some negative frequency component. That's typically how you define it. And so the idea is that the RMS square of these two together, so P hat R RMS square plus P hat I RMS square, this should equal to P square RMS. So the power in the signal, again these are appropriate measures of power that you have to see for yourself, is equal to, so there's no information lost in doing the Fourier transform. So Fourier transform preserves the information in the signal, and here information is power, okay, in a sense. Any other specific question that I can answer on this topic? Any big picture thing of why we are doing what we are doing, anything, or any particular detail that is still not clear? So I'll get into the next topic, which is uh, our propagation of sound waves. So throughout this course and even from the beginning, we have made a distinction between the source of sound, like you and me vocalizing out, and its propagation. All that nice business of linearity of acoustics, all that is applicable for the propagation part. The source is a bad business. Okay, it's much more difficult to figure out uh, what part of my vocal cords vibrations or my moving around, how is that affecting the entire sound field that you are hearing. If I were to muffle my mouth and so on, what is changing in the sound field is very difficult to figure because it's not linear. It is not easy. So this part is much more difficult. We will address this uh, towards the later half of this course. The propagation is a much simpler part, and that is what we will tackle first. And this is much more classical. So much of this that we are doing here is very classical. We'll touch upon a little bit of specific things for aeroacoustics as we go along, but not much. Okay. So if you know classical acoustics, then this is all bread and butter for you. So in the propagation of sound waves, we will be looking at 1D, that is one dimensional waves, because they are the simplest, and amongst them we will look at plane waves and spherically symmetric waves. We will see in going that 2D waves are a very different animal. They are not of the same kind as 1D and 3D waves. So where might you see 2D waves? Water waves. On the surface of water, if you drop a pebble on the surface of the water, the ripples that go out, that is a 2D wave. It's not acoustics, you cannot hear that, but the mechanics is same. And it turns out that the details of that 2D wave propagation are very, very different from our intuitive understanding of 1D and 3D waves that most of you will already have. Okay. So today we will talk about plane waves. So as I had already told you at the beginning, and maybe you would also appreciate this, that at heart, acoustics is just a subset of fluid mechanics. So we will be using our knowledge of fluid mechanics to derive the appropriate equations that are governing acoustics. And again, the main distinguishing factor is that it is linear. So for fluid mechanics, we of course begin from the governing equations. So governing equations are of course mass, momentum, and energy. So in your studies, you have studied in your studies of fluid mechanics, you have come across various forms of these governing equations: differential, integral. In differential, there are various forms. So what all differential forms do you know of? In differential forms of governing equations? No. Kinds of differential forms of the mass equation. Conservative form, non-conservative form, might have seen these things. Anybody does CFD? Huh? Yes, and but uh, so as opposed to, so the differential forms in conservative and non-conservative forms are different. Okay, so and then there are integral forms. So when we are trying to derive, our goal is to understand how does plane waves propagate. Uh, what do you think will be the appropriate form of the governing equations? to start with? Integral, differential. Okay, okay. So integral form, when would you use it? So what you are suggesting is that if we want to analyze gross behavior of flow inside and maybe affecting a control volume, then control volume or integral form is relevant. So in what sense might acoustics be amenable to control volume analysis? Would there ever arise a need for us to understand, say, acoustics from a control volume perspective? So if I were to say I'm only interested in, I'm going to send out this much of power, what do you receive? Okay. If it's such gross level of information, if I'm interested in, then of course that will be relevant. So in our derivations, we will also use the integral form, or get to the integral form as a way of making gross sense of what is happening. But uh, we will mostly be using the differential form because we want to get into the nitty-gritties of what is happening. So differential form gives us that level of detail. So plane waves, the name is obviously, I hope is clear, is where the wave fronts, and again we will talk about what are wave fronts more exactly, but wave fronts is something that you already have an intuitive feeling for, everybody, right? Anybody doesn't understand what is a wave front? What is a wave front as opposed to a wave? Same phase, perfect. So then comes the question of what is phase. So that there are, but these details we will work out. But so from a mathematical perspective, we will look at plane waves now, but the physical perspective is somewhat intuitive to you, that we are thinking of information propagating as planes. Okay, so every plane has got a different information content. So uh, if I were to be able to send out planes of same information content into space, then that will constitute a plane wave. If I were to instead send out spheres of same information content, then that will be, and multiple spheres of that, then those will be spherical wave fronts that I am sending out, acoustics or whatever might be the nature of those waves. Um, okay, so in that sense, we can think of, in the differential form, we will think of flows where pressure, say, as a function of x, y, z and time is actually just p as a function of x and time. There is no y or z dependency because again my model is trying to address a situation where there is no y or z variation of my information content, including pressure, velocity, density, temperature, all those variables are information, and nothing is varying in two directions, that is y and z. And so x is the interesting direction in which things are varying, that is the direction that is orthogonal to the or this is the x direction, where, so this is the same info or phase, the wave, okay. And there are more of them coming, so there is more such planes coming one after the other with different phase, but the phase is same on the entirety of the plane, and that plane is doubly infinite, so infinite in y and z. So this is the reality that I am trying to model, and we'll see where it is applicable very soon, and you probably have already heard about pipe acoustics. So flutes are the classical example of that. So similarly, your u, x, y, z and time will also be just u, x and time, and v will be identically equal to 0, w will be identically equal to 0. Now you can argue that what if we assume that v is actually, say, 1 meter per second. Can we have a planar wave such that v is 1 meter per second and say w is minus 0.5 meter per second? We'll think through these possibilities as we go along, but we'll see that it's okay to assume that these are 0 without any loss of generality. So we can say that without loss of generality, V is equal to W is equal to 0. And we have to prove that as we go along. So with this as our flow variables, the mass equation can be written in differential form as differential form of mass equation. Let me use capital V for the velocity vector. So that indeed is the mass equation. What it tells is that rate of change of density is accounted for by the dilatation of the flow, that is the increase in the volume of a parcel of fluid having constant mass. Okay. So that is what it's saying. So that mass is conserved. That's the idea. For our particular choice of only x dependency, we can simplify this and have only, and because V and W are 0, we can have uh, rho, sorry, so momentum equation will be del rho u del t plus del x of rho u square plus del p del x is equal to 0. This is going back to expecting that you are good with your fluid mechanics. So how might I write the energy equation that is going to help us? So you can write the energy equation in terms of the internal energy, enthalpy, temperature, even pressure if you are so inclined. What might you write it in terms of such that you get the maximum benefit? You want to derive the governing equation for acoustics. So what? Huh? Pressure. So let's leave it for now, and we'll come back to this to see what form might help us the most. Okay. So you have to remember about the characteristics of acoustics that are going to help us in this situation. So acoustics is not all of fluid mechanics; it's a subset. Because of the linearity, we have argued that some things are more important than others, and some things are negligible. So we'll come back to that. Okay. So what is our next order of business? Boundary conditions. Okay. Um, we'll come to that much later. What aspects of acoustics should we get into these equations? Hmm? Linearity. So this is a linear, right? This is non-linear. There's a quadratic non-linearity. There's a cubic non-linearity. We need to get rid of those. So we do the nicest thing possible, linearization. So we say that Pxt is equal to some P0 plus P prime xt. So what we are doing now is we are for a stationary medium. So we are deriving the equations for a stationary medium, and so these are the medium properties. So rho will be equal to rho naught plus u will be xt equal to 0 plus u prime xt, v xt will be 0, w xt will be 0. Again, I invite you to think through what will happen if you do not have these as 0. So we plug these into our governing equation. So I'll just write out the governing equation for mass. So it was dou rho t plus del x of rho u is equal to 0. So please linearize that using this simple decomposition. So because our velocity, or we'll call it the base velocity, so this base velocity is 0, So this becomes, and rho naught is independent of time. So this is simply dou rho prime dou t. Del x of rho is rho naught plus rho prime into u prime, because there is no u naught, and so the rho prime u prime is very small compared to all the first order terms. So this is a quadratic term. So this uh, so the rho prime u prime, so the rho prime gets cancelled out in comparison to the rho naught, and so you end up with dou rho prime rho naught. So this is your linearized mass equation. So I invite you to do the same thing for momentum. Momentum, if you have forgotten, I'll just. So what you're probably figuring out is that no matter what you do, this is a quadratic term because u is small, and so this is already quadratic, whereas this is linear. This you can linearize. So you will get rho naught del u prime del t plus del p prime del x equal to 0. So what might the um, energy equation look like? We want to simplify things. So what form of the energy equation will be the simplest? So what are the characteristics of acoustics that we are looking at? Isentropic. Isentropic. So you write the isentropic equation. What is the isentropic energy equation in differential form? In differential form, what will be the isentropic energy equation look like? Entropy, entropy. So energy equation, you want to write it as ds equal to 0. So your changes in entropy are 0. So whatever you are doing, if you are on this wave, then you will not encounter any changes in entropy. So this is the easiest one for us to work with. One of the things that we know from this is that our isentropic equations are all known. So we will make good use of them. So we are already in a very good shape. We have got equations in terms of 3 variables: density, velocity, and pressure. And 2 equations are there. If we just consider those 2, we've got, of course, got to use the energy equation to get it down to 1 variable. That's the simplest form possible. So I'll just write these things again. So mass equation was del rho prime del t plus rho naught del u prime del x equal to 0, and the momentum equation was rho naught del u prime del t plus del p prime del x equal to 0. So one way of getting rid of the u prime is to take the del t of this and the del x of this. In general, we will see that a more general and very useful way of looking at it is to take the divergence of this equation, which in 1D is just the del x. We will see that later on when we go to derive, say, in 3D, then it's the divergence of the momentum equation which is the most relevant thing to look at. And then you subtract. You subtract this from that. So what you get is del 2 rho prime del t2 minus del 2 t prime del x2 is equal to 0. You got down to 2 variables, but 1 equation, second order, of course. No getting around the fact, but we are all there, well on the way out there. So next, what we are going to do is again make repeated use of the linearity and also other things that is isentropic. So in that endeavor, we will write rho prime. You will remember that rho prime is rho minus rho naught. So we will write rho as a function of x and time as rho naught plus d. Okay. So now we are going to use the, isentropy that is the using the energy equation, but in a slightly roundabout, big picture kind of way, we can say in all of classical thermodynamics, each thermodynamic variable is a function of two other. So we can write rho is a function of pressure and entropy, and because entropy is constant, this becomes essentially a function of pressure only. That's the beauty of entropy, that density is just a function of pressure, and we know that relation. We are going to look at that soon. But even if you don't know that relation, just from the mathematics, you can write this as rho Taylor series expansion plus d rho dp at p0 times rho minus rho at p0 plus higher order terms. So doing a Taylor series expansion of density, which is just a function of pressure. So it's expanding the density about P0. That is excursions of the density from P0. Now, because we have chosen a consistent base flow state, my P0 is related to rho 0. So this is exactly equal to rho 0. And so this term is the density fluctuations itself. Forgot my Taylor series. P minus P naught. And so this is P prime by definition. So we are saying that rho prime, which is rho minus rho naught, is equal to, or approximately I should say, up to linear approximation, is d rho dp at p0 times p prime. So this will help us to replace the rho naught in our equation with p prime. Rho prime with p prime. So our equation till now is this, where we have got rho prime and p prime. We intend to replace this rho prime by this p prime. So what is this d rho dp at p0? Yeah. So we will get to that. The what I want to use, the basic fact that I want to use, is that in isentropic flow, is this a positive quantity or a negative quantity? I increase pressure, density should increase. There is no way around it. So all that I am saying now is that S equal to 0 implies that d rho dp is greater than 0 at p0. If you at any base pressure, this is a positive quantity, and let's just call it, or let's just define it as C0 square, where C0 is a number for us now. So C0 is a real number. We're just making use of the fact that this quantity is positive to define a C0 as the square root of that positive quantity. So I want to get to the governing equation for propagation of this acoustic wave. So we start with the governing equations of fluid mechanics, and that is mass, momentum, and energy. And then we linearize, because we are dealing with a simple problem, linear acoustics. So we simplify that, and we end up with these two equations. I want to solve it. So one way of doing it is to submit it to a CFD solver, but that defeats the purpose of this, or purpose of linearizing it, to make it simple so that we can access the solutions analytically. So in that endeavor to come up with a analytical result, we are making it simpler and simpler as possible. So to get rid of the velocity fluctuations from these two equations, we took this del t of the first equation, so that there is a del 2 u prime del x2 del x del t, and here also the same quantity, to so that we can subtract and get rid of the u prime. So we ended up with this. So now we have got a single equation, but there are two unknowns, density and pressure. So we want to get rid of one of them. So in that endeavor, we are noticing, or we are using the fact that for isentropic flows, my any thermodynamic variable is just a function of one other. In this case, density is a function of pressure. So I'm just going, and this is the where we bring in the physics, that this quantity is positive. We'll show that definitely that it is positive. So with this definition, that this quantity, so density fluctuations is some thing times p prime. I'll call it 1 by c naught square. Okay. No change, so just 1 by c naught square. Okay, so with that, I'll just substitute now. So again, writing out, we have del 2 rho prime del t2 minus del 2 p prime del x2 equal to 0, and rho prime is equal to 1 by c naught square p prime. So just substitute for that, and we get del 2 p prime del t2. So rho prime is 1 by c naught square. So bring the c naught square here. So this is the governing equation for pressure fluctuations in a plane acoustic wave. Your familiar wave equation. All of you have looked at this equation in your course on partial differential equations. So what is this C naught is not very difficult to comprehend. You all know what it is. It's the speed of sound, and how to derive it also you have seen multiple ways. Just because we are doing acoustics, I will be deriving that quickly so that I do not leave that part. But all of you have encountered this derivation in various forms and various courses that you have taken till now. So one way of looking at it is that let's say U tilde is the internal energy. Okay. There are various symbols for that. So one form of uh, one of the Gibbs equations is TdS minus PdV. So this is one of the Gibbs equations from classical thermodynamics. So we are going to use the fact that we are dealing with ideal gases, calorically perfect gases, and of course isentropic. So with isentropic, this TdS is 0. Du tilde becomes your Cv dt from your calorically perfect gas assumption, uh, and then you will recall that Cv is equal to R by gamma minus 1. So we have and of course your ideal gas tells you that P is equal to rho RT or RT by V. So with all these we have R by gamma minus 1. So this is du dt is equal to PdV for now. This dt we can write in terms of the P and V. So dt is equal to PdV plus VdP by R. So PV is equal to RT. So taking the derivative of that, we have this form. So we've got R by gamma minus 1 dt is PdV plus R cancels out nicely, and we have got PdV 1 by gamma minus 1. So I'll take gamma minus 1 here. So it will be gamma minus 1 PdV plus PdV plus VdP equal to 0. So this one cancels out with this one, and you have gamma PdV is equal to V minus VdP. So your favorite PV to the power gamma equal to constant term. Now, of course, what we want to get out of this is what we started out with, which was this C naught square. So we defined C naught square as d rho prime, d rho dp at P0 was defined as 1 by C naught square. So I want to connect that C naught square to what we have, and all of you know all these connections. So just going from there, gamma PdV equal to minus VdP. So dV equal to d of 1 by rho minus 1 by rho square d rho. So I got gamma P dV is minus d rho by rho square is equal to 1 by minus 1 by rho dP. Minus cancels out, one of these rows cancel out, and I get d rho dP is equal to rho by gamma p, which is of course 1 by C naught square. And not directly. So then if I want to specialize this to the base flow, then I will evaluate this at P0, and that will be rho naught by gamma P naught, and that I'll call as 1 by C naught square, so that I get the C naught to be root over gamma P naught by rho naught. So one of the many ways of coming to this conclusion, and also equal to root over gamma RT naught. So I'll just go back to what we have till now, which is that del 2 del T2 minus C naught square del 2 del x2 of P prime is equal to 0, and C naught square, C naught is equal to root over gamma P naught by rho naught is equal to root over gamma T naught. So this is our governing equation for planar acoustics in a quiescent medium, that is stationary medium. That is, the medium has got no base flow and it is uniform, of course. There is no variation of the medium in x or in x only, this is 1D. So the reason that you study these kind of equations in your PD course is because this is very often that you come across this, and you would have already got some ideas about how to go about solving these equations. So you'll exercise those ideas to solve. I think it's the first homework problem, to see for yourself that the general solution, and the interest is to, and you have to show it's a general solution, not a particular solution, but the general solution is given by D'Alembert, that my P prime as a function of x and time can be expressed as the sum of two functions where f and g are arbitrary twice differentiable functions of a single variable. So you will show that this is a general result and not a particular result, but in general you can find that the solution to this 1D wave equation, which for us is the acoustic wave equation that we are thinking of, is governed by or can be expressed in the form of this kind of two functions. Being a general form, it does not tell us directly the answer. Okay, I do not know what is f and g. You still got to find that out. We will see a quick example where you can find it out, but it still tells us a lot. What does it tell you physically now? So what he is talking about is this kind of idea, that suppose my P prime is given by an arbitrary function, if I can. So suppose this is a function. Suppose for the moment that g is equal to 0. So suppose g is equal to 0, so that this is exactly f. So if this is the form, then what we are assured is that let's take the value of this function at a particular time. This is time, or no, I'll take this as x. Okay. So let's take this pressure, this the particular value of p prime at t is equal to 0 c. So suppose we find that, so this is the picture at t is equal to 0, and I am interested in understanding what is happening at say t is equal to some capital T. So because my p prime is a function is f of x minus c naught t, what I am invited to do, because the g part is 0, what I am invited to do is to uh, figure out that okay, p prime at t is equal to 0 and at that x is equal to, so p prime x and 0 is f of x. So which is that value? So this is f of x. This value is the f of x. Now, if I am interested in understanding what is happening at capital T, then I am told that p prime x capital T is equal to f, the same function f at x minus c naught capital T. So, what I have to do is the value of f at this particular point x will be the same as what I would get, or at time capital T, I would have to go back to, okay, so let this be x minus c naught t. So if this is x minus c naught t, then what I am told is that uh, p prime at x of t. So if this is the picture at x of t, at x at this particular time, I would expect to see this value. So that's the value that I would expect to see, because that is the value of the function f at x minus c naught t. So this is the x minus c naught t on the x axis, and whatever is the value here, that is what I'll expect to see at x at this time. And so connecting the dots, what I would get is this as shifted version of the same function, identical. Huh. Bottom graph is of, no, this is just the p prime at t is equal to 0. This is p prime at t is equal to capital T. So this is what this equation, this functional form is telling us, that if g is equal to 0, then this is the picture. Okay. So now I would like you to think through this idea that suppose p prime at t is equal to 0 is again such a thing, and suppose p prime at t is equal to t is something like that. What is the expectation at 2t? So these are snapshots of the wave that you are taking at t is equal to 0, at capital T, and at 2t. You are taking snapshots of the wave. And so what do you expect this picture to look like at 2t? So I drew two pulses at capital T. That's the catch. So there are two pulses at capital T, but only one pulse at 0. So we were talking about this f function, which is the rightward traveling wave, right? That's what we figured out from this, that f is the rightward traveling wave. It just travels at the speed c naught. So you have to remember that there is also, in a general solution, there is also the leftward traveling wave. So if this is p prime at t is equal to t 0, and this time f is equal to 0, then at a later time this would have moved somewhere here. So it should be a consistent speed, okay, c naught. So this is the g function. Okay, so this is the g function, because if you put t is equal to 0 in the g function, then this is what you will get, p prime is equal to g of x. So there is these two parts, and what we are saying here is that this one wave, it has apparently broken up into two parts. That means at t is equal to 0, those two happen to be together co-located, and of course not equal or nothing more than that what I am saying, but apparently two parts came out and they are going in opposite directions at a later time. So at an even later time, you would just expect these guys to go further out and nothing else to change. In particular, they should not change in shape. That's the basic premise of this 1D wave solution given by D'Alembert, that this f and g, the shape remains preserved. They are just traveling leftward or rightward, the two of them. It is the pressure, but that is the p prime. So this is the p prime. So p prime comprises of two parts. One of them is a rightward moving part, one of them is leftward moving. In this cartoon, I just clamped down on one of them and said that there is no rightward moving part, so it's purely leftward moving. That is what this tells you, that this f function is the f function, whatever it is. You are just going to evaluate it at different times, so that is just going to give rise to a shift in x. Okay. So it's the same waveform, just moved, propagated. That's the essence of propagation. So in propagation, a plane wave, again this is under the simplifying assumption that there is isentropic, it's of course linear, so inviscid and all that. So with all that assumption, what we are finding is that our acoustic wave doesn't suffer any change in shape. So we know that these long slender pipes like the flutes, and also maybe a pipeline carrying gas, all of these support these longitudinal or waves. So this is a long pipe. So that long qualifier, we'll see why that is relevant. So we will come to that in a moment. Let's assume that this is a long pipe and there is a piston at one end which is having a velocity as a function of time given by capital U. So if you assume that x equal to 0 is the nominal location of this piston, and this piston is making back and forth motion around that with arbitrary signal, but nominal location is there, then I want you to find out p prime as a function of x and time anywhere to the right of this. So x is increasing rightward. Again, x equal to 0 is the nominal location of this piston about which it is making arbitrary motion, not with a single frequency, nothing like that, just the nominal location is there. So what would the pressure fluctuations look like if all the assumptions of the prevailing theory, that is linear acoustics, is planar waves, is valid? U is the velocity of this piston as a function of time. Just change one small change. Let's just be interested in the velocity for now, u prime. We'll come back to p prime soon. Okay, so I'll make one statement and then justify that soon. The statement is that for such planar acoustic waves, your density fluctuations is proportional to pressure fluctuations. Your velocity fluctuations are also proportional to the pressure fluctuations. And I'll just remind you that we have seen that pressure fluctuations as a function of x and time is given by this form. So for now, all that we are going to make use is that u prime as a function of x and time is also given by, say, h of x minus c naught t plus, let's say, k of x plus c naught t, two arbitrary functions which are scaled versions of f and g through this proportionality constant. So what he's finding is that this is capital U of t minus x by c naught, and we can get this heuristically for now. Later on we will get it exactly using much more mathematical rigor. So right now what uh, he's possibly thinking about is that this is a close fitting piston inside a cylinder. So whatever information this is creating in this medium is going to propagate. If you are a rightward, if you are a point in the rightward part of the pipe, you are only going to get this guy. You cannot get any part of this because that is information that is propagating leftward. So our solution must be of this form, f of x minus c naught t. Now what we are going to do is we are going to write stylistically that u of t is equal to u prime at t minus or so. The other idea is that the fluid medium that is interfacing with this piston, that is going to have the same motion as the piston. Why not? There is no vacuum in there. Right? So whatever fluid particles are there are going to have the same motion as this piston. So other thing that we are assuming is that this, and again these are things that you have to specify in order to get this thing to work, is that this displacement of this piston is not significant. So that we are in the linear regime. Significant with respect to what? Significant relative to wavelength. That was the relative, that was the characteristic length of this acoustic wave. That's the wavelength. Okay. So the displacement, if it is insignificant relative to the wavelength, then we can ignore that displacement and assume that u prime, the particle velocity at x equal to 0 and at time t, is given by the piston velocity. So again these are little niggling things that you do, which is all okay in the bigger picture of modeling, is that you assign the particle velocity at x equal to 0, although your this face is not at x equal to 0 all the time, but you do that little cheating in a sense, and it is okay in the bigger picture of trying to understand what is happening at a faraway point. That this velocity, the particle velocity at x equal to 0, but at any time t is given by the piston velocity. So if that is the case, I am going to write this stylistically at as t minus 0 by c naught, and u prime I want to bring it in this form. So I recognize that what this form is x minus c naught t. I can write that as minus c naught times t by t minus x by c naught. So instead of evaluating x minus c naught t, it is equivalent to evaluate this function. So this is of this form, that at x equal to 0 my velocity fluctuation is of this form. So that's why we can write this as a heuristically derived solution for the particle velocity, that we just replace now the 0 with x noting the similarities. Okay, we are just doing that vague hand waving thing. Again the definitive solution is much more non-trivial, but you will get to the exact same answer. Okay, that's going to come maybe closer to mid-sem. Okay, so we have to develop the mathematical tools to get there. But heuristically, this is what is happening, and it's not very surprising. What we are saying is that whatever information is created by this will take some time to propagate. What is that time? That's given by the speed of sound. So, and whatever information is created here is going to come here. There is no information loss because it's a planar acoustic wave. There is no information loss. So whatever this guy is going to be doing is going to be felt here, but after some time, which is what is given by this. So after what time? X by c naught. So if this is at x, then the time delay of information reaches that x by c naught. That's not surprising. So physically it makes a whole lot of sense. So back to Navier-Stokes. So bye bye. Okay. No acoustics. You can go to your Navier-Stokes class. So that's the beauty of acoustics. I choose what problems I'm going to address. I'm not going to address your problem because I cannot. It's not acoustics anymore. Okay, so I'm going to just now justify these two parts and then close today. So the first part is very trivial. We have that P prime, or we derived this actually, that rho prime. So we derive that rho prime equal to 1 by C naught square P prime. Remember that C naught is equal to root over gamma P naught by rho naught gamma T naught, which we choose to call the speed of sound because sound waves are apparently moving. The information in the sound wave is propagating at that C naught speed. That is what we found from the solution, and that's again your homework problem to get that mathematically. So because of this, so the constant of proportionality is just 1 by C naught square, quite trivial. What do you do with the velocity? So it's being claimed that U prime is also proportional to P prime. How do you see this? You have to go back to the basics. Basics are mass equation, momentum equation, no getting away from them. So your mass equation was that del rho prime del T plus del rho naught del U prime del X is equal to 0. So we have already found rho prime is as a function of P prime. So we are going to use that, and for now we are going to derive the relation between U prime and rho prime. Or I might just write this as rho prime is 1 by C naught square. So del P prime del T plus rho naught C naught square del U prime del X equal to 0. So if I want to find out U prime, I have to integrate this equation. Because there's a partial differential equation, I have to do a partial integration. So I'll write it as U prime as a function of x and time is the partial integral in x, because that's what the partial integral is for, in x of 1 by rho naught C naught square minus del P prime del T dx. So we are discussing what is the relation between velocity fluctuations or the particle, what we call the particle velocity. So this U prime is called particle velocity to distinguish it from the sound wave velocity, which is C naught. So we are trying to relate that to the pressure fluctuations for which we have got the solution. So this is acoustic pressure fluctuations in the sound wave. We are going to relate the other thermodynamic the flow variables, density and velocity and temperature, if you so please, to the pressure. So that once we get a solution for pressure, we can automatically get a solution from unit, just like we get for density. I'm missing that this is from 0 to x plus some h of t, right? That's the partial integration. So we are doing a partial integration in x. The constant of integration is not really a constant, it's a function of time. So this is partial integration. Now I'm going to do another hand waving thing. I'm going to separate the problem into two parts. Again, using D'Alembert's contribution, that I'm going to first consider that P prime is just f, there is no g, and then I'll let you guys figure out what will happen if it is just g, no f. So that will help us get the derivation faster. So we will say that let P prime x t be exactly equal to just f of C naught t, that is a rightward propagating wave. For this we can derive whatever we are after, and separately we will look at later we will let P prime be just equal to g and then not have the f. So we will combine these two solutions at the end and get a consistent solution that is going to be valid for an arbitrary wave having both leftward and rightward propagation parts.